Hello everybody, this is Professor Carlos Torres Verdin, broadcasting live from the beautiful hill country of Texas for Principles of Formation Evaluation, PGE 358, Spring 2020. Today we are going to introduce and describe in very much detail the procedure that is normally used to evaluate, to analyze the petrophysical properties of shale-laminated sandstones. I'm going to be breaking up the lecture into two sections. The first section is going to be a PowerPoint presentation that will guide you through the principles, concepts, methods, step by step of the equations that we use to analyze every single component of the process, beginning with the analysis of the water saturated section of the well to calculate electrical resistivity of formation water. And then we will move over to a hydrocarbon bearing section. We will calculate all of the properties, which are sandstone porosity, sandstone hydrocarbon saturation, and the density of the hydrocarbon. We will conclude with a few comments, and we will implement the calculations and method using one example of a turbidite sedimentary sequence in the deep water Gulf of Mexico, which we have covered in class, and that will be the second part of the lecture. I hope you enjoy it. I hope you're well. I hope you're happy, and let's get going. Hello everybody, here we are with a brief introduction to the exercise that we're about to perform. Let me just say, this is going to be a step-by-step example exercise for the calculation of storage properties of shale-laminated sandstones via well logs. This example is based on pages 1 to 3 of the well log compendium part 2. What we're going to do is to calculate net to gross first, then sandstone porosity, that is the porosity of the sandstone, interbedded sandstone layers that we have in shale laminated systems. Then we're going to have the calculation of the hydrocarbon saturation in the sandstone layers. We're going to calculate the hydrocarbon per volume, and last but not least, the corresponding hydrocarbon density. And along the way, I'm going to introduce some comments as to how to verify, check, vet, and interpret the calculations so that they truly make sense. Slides that we're about to see are just the introduction. I want to say that we have also material that goes with this lecture, the PowerPoints that are annotated here. I mentioned the pages of the compendium. I also suggest that you read chapters 8 and 9 of the textbook, where all the formulas are derived and physical intuition is given behind equations. Last but not least, on Canvas, I posted some class handouts, and those class handouts indicated here are going to be the basis of the lecture today. So please make sure that you download all this material, or you consult this material before the presentation, during the presentation, or after the presentation, whatever suits your needs better. And I also want to make sure that you know that all the equations that I'm going to present in this lecture, as well as in other lectures for PGE 358, those equations are all carefully described and explained in the appendix of the textbook, where I have a lot of detail. And second, in the second to last section of the compendium part 1, you can find them. Also, I want to say that the last section of the well log compendium part 1 includes several examples that are complete step by step of all the algorithms, methods, equations, assumptions, illustrations of the method that we're going to cover today. And there are two examples in that compendium. So I invite you to take a look at them. If you have questions, they're beautifully explained and they're very easy to follow, and they are based on cases other than the ones that I'm going to be showing here. Good. First of all, let's think about the issue here. The issue is that we're dealing with laminated systems, shale sandstone laminated systems. The systems can have or be observed by well logs at an angle. In other words, there's never guaranteed that the well is going to intersect these layers at 90 degrees. The layers will always have a non-negligible dip and azimuth with respect to the borehole trajectory. So it's important to understand that, and it's important to understand the length, the thickness of these layers in the context of the volume of investigation of the measurement. So very often I have this slide that indicates what the volume of investigation of the measurements is, and of course that volume depends on the particular well log that we're looking at, but in essence some of these features are smaller than the volume of investigation, so the measurements either have a direction depending average or a volume depending average, and we have to do that in the context of the rocks that we're looking at. Such as in this example, sometimes the rocks are thick enough so that they can be seen perfectly well by the logs. The properties can be properly analyzed. We don't have to make any assumptions. We can take the logs for face value and do the calculations with them. But as we go into smaller and smaller layers at the bottom of the sequence, then the volume of investigation of the measurements is larger than the size of the layers, and because of that we have to remind ourselves that the measurements are a volume average of those properties or a direction depending volume average of those properties, and that's important. We have also amplified views of shale sandstone laminated sequence. One of the assumptions that we have in rocks like this that are below the volume of investigation of the measurements is that all the layers, these shale layers that we have here in the volume, they're all assumed to have the same properties, and same with the properties of the sandstone that we have within that volume of investigation. Of course, this doesn't mean that all of these layers are going to be the same everywhere in depth, because as you go different depths you will have different shales, and also you will have different properties of sandstone and also different saturating fluids. And the other thing that I have been talking about is what is a pure shale end member of the sequence. We have to locate that because that's going to give us a reference, and that reference is going to be the one that we are going to be using for the calculations. The other thing is to remember that these sandstone laminated sequences, we are sandstone shale laminated sequences. We're assuming that they are the combination of two end members, the pure shale end member and the sandstone member. And when we do calculations of net to gross, essentially we're looking at the fraction of the sandstone of the volume of sandstone within a reference volume of investigation. That's what we have to take into account, and in this analysis we are after the properties of those sandstone layers. We want to know whether they have good permeability and good porosity. Permeability, of course, will be an indication of the grain sizes, and also we want to know if those sandstone layers are saturated with hydrocarbon, and what is the hydrocarbon saturation, and what is the hydrocarbon pore volume of the rock. That's important. And in the previous presentation we talked about the Thomas-Tibor diagram, which essentially is a mixing law for porosity of the rock and volumetric concentration of shale, where we're doing mixing between the two end members and volumetric concentration of shale, here indicated as CSH, is nothing else but the fraction of the shale layers that we have in a given volume. So that's what Thomas Tybur says, that if we have a laminated, a shale laminated sequence, the total porosity rock is a weighted average of the sandstone porosity and the shale porosity, where the weights are given by their volumetric proportions. And second, those mixing laws, linear mixing laws, apply to both the gamma ray log and the density log, as shown here. So we have mixing law for the gamma ray log, where we have the gamma ray log measured in the pure shale and the gamma ray log measured in the clean sandstone. And the gamma ray log that we measure is an average of the two values, where the weights of the average the sum is equal to 1, and they're equal to the volumetric proportions of each one of the members. So as the volumetric concentration of shale increases at a given point in the well, then the value of the gamma ray log for shale dominates. But if we're going into a clean sandstone, then the gamma ray log value of the clean sandstone will dominate in the measurement. Similarly, for the density, if we measure the density of the rocks, we see that the density will be a volumetric average of the two end members, the density of the sandstone and the density of the shale. And if the sandstone has, in that volume, has constant properties for the density of the grains, the density of the fluid, and the density and the porosity of the sandstone, then essentially we can assume that within that volume the sandstone the density of the sandstone remains constant. So we go with that. All right, let's go moving. So let me just introduce a synthetic example that I'm going to be using in this quick PowerPoint presentation to illustrate, to highlight and emphasize the most important points. There are two components of this synthetic example. I have one rendering in which all of the sandstone layers here are water saturated. And subsequently, I have one in which all the sandstone layers are gas saturated. But in this example, what I want to point out is the following. Here we have three important tracks. The gamma ray log track, then we have the neutron and density porosity track, where both the neutron and density logs are expressed in sandstone porosity units, and that's a matrix that we expect the two to be given when we are analyzing a siliciclastic sedimentary sequence. And here we have the electrical resistivity logs in logarithmic scale. Here we go from 0.3 ohm meters all the way up to 30 ohm meters, and I have two logs. But let me explain what these logs are, because we have not seen them before. The black color log is a standard resistivity log, which is a resistivity parallel to bedding plane. And the red color log that we have here for the first time is the resistivity perpendicular to bedding plane. Look at this. So let me come back to this in 1 second. But let's see at the gamma ray log, based on the gamma ray log, and also based on what we see in the neutron and density logs and the resistivity logs, we understand immediately that here we have a shale at the top. It's a pure shale. And then we have another pure shale at the bottom. That's what we see. And because of the values of gamma ray log that we have there, and also because of the values of neutron and density logs that we have there, and because of the values that we have of resistivity at the top and at the bottom, we immediately recognize that the shales have, the two shales at the top and at the bottom, they have equal properties. Good. Second, because the resistivity parallel to bedding plane and perpendicular to bedding plane are the same, that means that that shale is isotropic. Now, let's move on to see what happens with the sandstone. When the gamma ray log exhibits the lowest values of the sequence, those are the lowest values, And to remind you, this is water saturated. What we expect is that if for those lowest values of gamma ray log, the rock, the sandstone is shale-free, what we expect to have is that the neutron and density logs expressed in sandstone porosity units should overlap. And lo and behold, that's what happens. So when we have the lowest value of gamma ray log, we immediately see that the neutron and density logs overlap, and the value at which they overlap is the porosity of that sandstone. So in this case, we have 60 porosity units across, then we can immediately calculate what the porosity of this rock is at that particular value right here. And just by reading this segment, and it's immediately understood what the value is here. Same here, and just by comparison, we understand that whenever we have a clean sandstone, the values of the porosity, the values of the porosity of that sandstone seem to be the same over here and over here. That's actually a very important remark. Now, what happens when the gamma ray log begins to increase over here? Well, two things happen. Several things happen actually. Number one, immediately we see across that the neutron and density logs no longer overlap. In fact, the neutron log exhibits larger values, larger apparent porosity values than the density log. We have a difference. Second, look at what happens with the resistivity logs parallel and perpendicular to bedding plane. We have a difference, which was not the case at the bottom, where we had a clean sandstone. What's going on here? Well, what's going on here is that the reason why the gamma ray log has increased over here is because the sequence that we observe here is actually a shale-laminated sequence. And because of that, within the volume of investigation of the measurement, we have small layers of shale, small layers of sandstone, and those have given rise to electrical resistivity and isotropy. Now, the electrical resistivity is one perpendicular to bedding plane and one parallel to bedding plane. So those laminations are invisible, if you will, just because the volume of investigation of the measurements is larger than the individual layers. This is like, say, Antoine de Exupéry, which says in the Little Prince, the Petit Prince, says that the important things are invisible to the eye. Here we have something that is essentially invisible. We just see that the laminations exist because they're manifested in the separation of the neutron and density logs, and because we have an isotropy in electrical resistivity. Now, as we go along, that separation between neutron and density logs increases because the volumetric concentration of shale increases, the degree of anisotropy also increases. Now we go to the next member of the sequence, which is shaly, because the gamma ray log is not as low as with the other members right here. And even though it's water saturated, what we see is that the neutron and density logs do not overlap. You see, the neutron is larger than the density. And then here we have presence of anisotropy. Now we go on and we go to the upper sandstone member, and what we see is we have the lowest values of gamma ray, and again we observe overlap between neutron and density logs. That means that at that point we have a clean sandstone, which means that we have zero presence of shale laminations, and the resistivity logs exhibit the same values. We don't have an isotropy. Now in this example, the water is a brine, is a salty formation water, and in this example, the resistivity of the water saturated sandstones is lower than the resistivity of the shales. We are below the shale baseline, which is another behavior, which is consistent with the fact that we have good porosity in the sandstones and we also have a salty brine. So let's that example. Let's keep that. Now let's go to the same example, but now automatically let me populate that sandstone, that sequence, entire sequence with gas. So what we see here is, of course, the gamma ray log doesn't change because the gamma ray log is independent, insensitive to the presence of the fluids here. So it will remain the same with respect to the previous example, but look what happens with the neutron and density logs. So now we have, whenever we have a clean sandstone, that we saw that it was clean because we had a way to understand how it behaved in the presence of water, and water gave us the hint that it was clean because the neutron and density logs overlap. But now here, the clean sandstones, we have a beautiful crossover where the neutron porosity is lower than the density porosity, and the yellow highlighted sections are indicating presence of fluids lighter than water. So we see that. But as we walk along this sequence, the gamma ray log increases because the volumetric concentration of shale is increasing, because we have more lamina of shale than lamina of sandstone. So at some point, even though it's gas saturated, the crossover decreases. It's actually gone. Now the neutron is larger than the density, so this behavior tends to be similar to the behavior that we have in a pure shell. You see, when we increase the volumetric concentration of shell in any of these shale-laminated sequences, the tendency for the logs is to begin to look like the logs across a pure shell. That's what we see here. And as we go along, that the difference between the neutron and density increases. Now we hit again a sandstone, which is shaly, and then we see that the crossover shows up again. Interesting, isn't it? And then gamma ray log increases. That means the volumetric concentration of shale increases. The crossover is gone, even though we continue to have gas. And then over here at the top, clean sandstone, crossover comes back. But I also want to show you what happens between the resistivity parallel to bedding plane, that is one in black, and the resistivity perpendicular to bedding plane. We see that now, as the volumetric concentration of shale increases, the degree of discrepancy between the two increases, which means that the rock becomes more anisotropic. This degree of anisotropy actually is larger than what we see with the water saturated version of this example, because the values are different, and also because the discrepancy between the resistivity of the shale layers with respect to the resistivity of the sandstone layer increases. I'll talk about this in a second. We see the same anisotropy above, but when we go back to the clean sandstone, that anisotropy goes away. So this is what we expect. So these two logs were designed to illustrate differences. Please keep them in mind, and let's go on with the analysis. One of the things that we do now when I place them together, the two versions, the water saturated version of that rock, and the gas saturated version. This is the nice thing that you can do with synthetic examples, that automatically you can populate it with the fluids that you want, and then you can calculate the corresponding well logs, and then see the differences. And for instance, in the case of gas saturated sandstones, that we can see that in the clean sandstones, the electrical resistivity is, their electrical resistivities now are above the shale baseline, which is consistent with the presence of hydrocarbons that we have seen before. But what I want to mention is the following. Sometimes when you are dealing with shale-laminated sequences, very often it's really hard to find a clean sandstone like this. It's really hard. Very often what you have is a shaly sandstone. It's almost like you had something going from here to here. So this section doesn't exist. So what happens when something of the nature happens? Well, now what we need to know is we need to identify whether for that minimum value of gamma ray log that we see here, what we have to know is whether that sequence is or is not clean. And the way to understand is always go to a water-saturated sandstone. We use that as reference, and for this, what we see is that for this value of gamma ray log that we see here at 3140, the neutron and density logs separate where the neutron is higher than the density, and that distance is an indication of the shaling. It turns out that if you want to calculate the volumetric concentration of shale here, there's a magic formula that I'm going to derive in a second that says, okay, measure the discrepancy between the neutron and density logs. That's the lowercase z. Now, go to the pure shale point and measure the discrepancy between the neutron and density logs. That's the capital D. So it turns out that if you want to calculate the volumetric fraction of shale here, what you have to do is to divide D by D. You see? This lowercase d will have to be smaller than the uppercase d, unless this is pure shale. What it means is that this lowercase d can go from 0 all the way up here, all the way to the top. But you see how it goes from 0 when the gamma ray log is minimum, and it goes to a maximum close to the value of the shale when the gamma ray log increases to be similar to that of the shale. So we have that difference. And so that ratio is one alternative way to calculate the volumetric concentration of shale, as I'm going to indicate. But that ratio, I have to remind you, only works, this procedure only works when all the sandstones in question here that are shale laminated are saturated with water. It doesn't work if they were saturated with hydrocarbon. Good. Now, based on the Thomas-Diver diagram and the mixing laws, we know the following. That it turns out that if you want to calculate the volumetric concentration of shale, it is relatively simple. Because if you go back to the mixing law that we had before, let me just go back a little bit, slides here. Well, if you go back to the mixing law that we had before, which is this mixing law here for the gamma ray log, right here, this mixing law. The mixing law says, okay, you tell me what the gamma ray log is in a pure shale, you tell me what the gamma ray log is in the clean sandstone, and I can tell you how to calculate CSH if you give me the gamma ray log. So solve this equation, and the solution of that equation that comes is precisely this formula that you see here, right here. That formula is the realization of the mixing law by turning the equation so that you make the assumption that you know what the gamma ray log is in the pure shale, you know what the gamma ray log is in a clean sandstone, and if you measure the gamma ray log anywhere else, then you can calculate the volumetric concentration of shale at that point. That's what this diagram here on the left shows. Essentially it says find the clean sandstone, measure the gamma ray log in the clean sandstone. How do we know that it's a clean sandstone? We have to have confirmation by looking at that gamma ray log in a water saturated sandstone, and we have to see that the neutron and density logs overlap there. And then we go after the shale baseline, which essentially we're looking at the values of the gamma ray log in a pure shale. If I go back to the synthetic example here that we had, what I'm trying to say is here, you first find the pure shale, maybe over here, maybe at the bottom, and then you read what the gamma ray log is here for the pure shale. And then you find the value of gamma ray log for a clean sandstone, and that has to be not only the minimum, but the minimum at the minimum in a water saturated sandstone, we have to see that the neutron and logs overlap. So not because the gamma ray log is the minimum across the depth section that we're studying, it doesn't necessarily mean that for that minimum value the sandstone is shale free. No, we have to calibrate it in a section that contains water. And the calibration means that we have to verify that the neutron and density logs overlap. Once I know that, then I'm very happy and I can go back to this equation and What it means is that now that I know the end members, gamma ray logs, now point by point, here, point by point, I can calculate the volumetric concentration of shale. This equation, mind you, it only applies to the case of shale-laminated sandstone. If you are going to a case that you have grain coating clay, then that equation has to be modified. But for now, we're safe because we're only looking at shale-laminated sandstones. Now, what happens if you don't have a clean sandstone? Well, don't despair, because we have an alternative way of doing it. And the alternative way, basically this equation, what you see here is the realization of my formula that says lowercase d over uppercase d. What this means is the following. When you don't have a clean sandstone, what happens is you don't have access to this section of the curve right here. But what we do is we go to a water saturated sandstone, we measure the gamma ray log in the water saturated sandstone, and we calculate the volumetric concentration of shale in that water saturated sandstone by calculating the ratio of lowercase d over capital D, as I indicated before. That ratio is evaluated here with the formula highlighted in yellow, which means the upper part is the lowercase d and the lower part is the denominator is the uppercase d. And the variables are expressed over here. So one is for the measurements across the shale and one is for the measurements of neutron and density log across the water saturated sandstone. And once we have these 2 points here, we can reconstruct the equation of the line here. And that equation, it's very simple to calculate, but if you have problems with, it's in the textbook. So please go ahead and check that. But that allows us to reconstruct that linear trend of the mixing law. How does it come? Very simple. Let me just explain you. This is and actually will come, that equation, so that you know that it's not coming from thin air, it will come in a minute just by looking at the mixing laws. So let me remind you, the mixing law for porosity and volumetric concentration of shale is here. That is the realization of this formula or this diagram here, which means that in shale laminated sandstone you have 2 end members and the total porosity of the rock is a linear mixing of the 2 end members, the 2 porosities, where the weights are proportional to or given by the volumetric concentrations of the 2 end members. So if you solve that equation, you take that equation and you solve for sandstone porosity, this is what you get. So let's say that you measure the total porosity and you know CSH, volumetric concentration of shale, then with this formula we can calculate the sandstone porosity. That is the porosity of the interbedded layers of sandstone, which means that we have to divide by 1 minus CSH. Please note that this division may become unstable if CSH is very close to 1. But we need to know the porosity of the shale and we need to know the total porosity. So how do we know the porosity of the shale and how do we know the total porosity? Sometimes we know, sometimes we don't. But if you happen to have the neutron and density logs at your disposal, which is what we have, we do that calculation by solving a system of 2 equations. Let me explain. We actually apply this equation, the mixing law for sandstone, to both the neutron and the density logs. And how do we implement it? In place of total porosity, we include the neutron porosity or the density porosity, depending on the case. Now CSH is here. How did I calculate CSH? Well, this calculation of CSH came from the linear plot that I showed before, which was this. That linear plot, the realization of that linear plot, or this equation right here is how we calculated CSH. Then we go here, and that's the calculation. It's in the denominator. And then in place of the shale porosity, we're going to include the readings of the neutron porosity log across the pure shell and the density porosity log across the pure shell. And what you are going to see is very, very interesting. Before you make this correction, the neutron log will be almost invariably larger, give you larger process, apparent process than the density log. But when you make this correction suddenly, the neutron corrected log will be less or equal to the density porosity log. And then here we will be very happy, because if we had hydrocarbon, now the neutron log corrected will be, the neutron porosity log corrected will be smaller than the density porosity log corrected. If they are equal, that means that we have in water, we're in water. If by any chance when you apply this correction the neutron log is larger than the density porosity log, then that means that you made a mistake in the calculation or some of your assumptions are incorrect. We'll come back to this. But now that you know this and you say, okay, now the corrected neutron is lower than the density log. So what am I going to do to calculate the porosity of the sandstone fraction of that rock? Then we apply this approximation that we have been applying for clean sandstones, which is the square root of the average of the squares. And that formula comes from behavior of neutron logs, an approximation that was derived by some gentleman that worked for Schlumberger. The derivation or the description of this is in the textbook, but essentially now we have a very good approximation of the sandstone porosity. Easy, isn't it? Well, we're going to apply it. Now, I told you that when you have a sandstone, a shaly sandstone or a shale-laminated sandstone saturated with water, we can calculate CSH with the formula that says lowercase d over uppercase d. Now I'm going to show you where that formula comes from, and it comes from here. So we do the correction for the neutron log as we did before. We do the correction for the density log as we do before. But we know that if the correction is properly done in a water-saturated sandstone, so what happens if I implement this formula in a water-saturated sandstone? So if the corrections are done properly, the selection of the pure shell is properly done, then what happens is this, that after making the corrections, the neutron corrected log should be the same as the density corrected log. And the values will be actually the values of the sandstone porosity. So if you enforce that equation, what's going to happen is this. Take these two equations, equate them, and now you can solve for CSH. And that's what this formula does. You take the two equations, you equate them, and solve for CSH. I have included here a subscript to indicate that this only applies to water. And then you get this equation, which essentially is the equation that has lowercase d over uppercase d. That's what it is. So it comes from there, from the correction that we applied in a shale-laminated sandstone for both neutron and density logs, and we know that if the correction was done properly, then at the end both corrected logs should be the same, equal, and that will be the sandstone porosity. And as a consequence, now we have an equation to calculate volumetric concentration of shale. So this equation should give you exactly the same values when you apply it to the gamma ray log, but this is just an alternative way of doing it. So here we have two possibilities. Just to remind you, we have two possibilities. One is to use the gamma ray log to calculate CSH using that linear mixing law, but that requires that you have a clean sandstone. Of course, we always have a pure shell, but what happens if I don't have a clean sandstone, but I do have a sandstone saturated with water? So then what I do is I read the gamma ray log in that water saturated rock, and then I calculate the CSH in that water saturated rock using the equation that I just derived, the lowercase d over capital D, and that gives me the 2 points now for the line. And the only thing that I have to do now is to reconstruct the line. So if I give you any gamma ray log, I can bounce this off this chart and give you the corresponding CSH. That's what we do. Now, Let me mention another difficulty in this analysis. So far so good. So far we have calculated volumetric concentration of shale. So far we have calculated the porosity of the sandstone fraction of the rock. We are so far. But now, what if we want to calculate the water saturation of the sandstone fraction of the rock? So here comes something very, very interesting. And that something is as follows. Now, we have to deal with a very important technical concept, which is electrical anisotropy. And I'm showing you these diagrams to illustrate the cases where we have rocks that have intralayers of shale and intralayers of sandstone. The volumetric concentration across these rocks is not the same. These are core photographs. This is another piece of rock shown here with a meter. And what happens is that anywhere you look at it, within the volume of investigation of these logs, which is, look at this, a number of inches, we have 3 to 4. Obviously, most of the logs are going to average through all this whole thing. What we're doing is averaging properties that have different end members. And when the property is a scalar property, well, the volume is what's going to account. But if you have an electrical resistivity or permeability, for instance, then these properties become direction dependent, and because of that they become anisotropic. So in cases like this, two examples, if you measure the electrical resistivity, what you're going to find out is that the electrical resistivity of these rocks is now direction dependent. You will have one direction parallel to bedding plane, and you will have another electrical resistivity perpendicular to bedding plane. Those two, same here. So the question is, okay, so now that I have the two, what do I need to do? Which one do I need to do? This is parallel to bedding plane, and this is perpendicular to bedding plane. So which one do I need to use in Archie's equation to calculate the sandstone hydrocarbon saturation? And that's what I'm going to talk about now. Let me give you this beautiful example here that illustrates the principle. Let's assume that you have a vertical well and you have horizontal layers. And in this example, we have, within the volume of investigation of this tool, we have laminations of sandstone, which are the light ones, and we have laminations of shale, which are the dark ones over here. And this diagram has been done so that CSH is 50%. So we have equal proportion of sandstone and shale. Okay, now what happens here is that if you use the standard resistivity measurements, they are actually designed to make an average across the formation. You have a volumetric average that is going on here, but essentially the measurements have been designed to enforce electrical current parallel to bedding plane, or if you want, perpendicular to the direction of the borrow. That's how the instruments were originally designed. Nowadays, we have a new set of instruments that allow you to also measure the electrical resistivity perpendicular to bedding plane. It took a long time to produce those tools, but now they become commercial. With that said, let's go to the next slide. This is what happens. When you have your instrument and your instrument is able to measure electrical resistivity perpendicular to bedding plane, then the measurement, now the electric lines will traverse through both layers of shale and the layers of sandstone. And the average, the direction depending average, now it will depend on the electrical continuity that we have across these layers. Does it remind you of a circuit in series? That's what it is. Whereas the measurement that is parallel to bedding plane becomes analogous to a circuit in parallel. Let me explain that. Okay, so here's an example. Suppose that you are in a turbidite sedimentary sequence and you have 50% proportion of sandstone and shale, and that this rock, the volume of this rock, is the volume of investigation of the tool. So all of these very thin layers of sandstone and very thin layers of shale, all of them are below the resolution of the measurement. Okay, but just for discussion here, let's assume that the shale, like we see in the deep water Gulf of Mexico, they have a resistivity of 1 ohmmeter. Let's assume also that the electrical resistivity of these intralayers of shale is the same electrical resistivity as the pure shale shown here. But let's assume that the intralayers of sandstone that we see here are hydrocarbon saturated. In that case, the resistivity of the sand is larger than the resistivity of the shale. Of course, this resistivity of the sand comes from Archie's equation. So if you tell me what the porosity of this sandstone is, what the RW is, what the A, M, and N parameters of Archie's equation are, then I can calculate what the electrical resistivity is. And of course, I also need to know the water saturation, so I can calculate. But just think of this as a thought experiment. Now, suppose that you make your measurements, and the measurements are either you have a tool that enforces induction coils here, so you enforce and induce electrical currents that are parallel to bedding plane, or you may have the other one. But when you do that, when you enforce electrical currents that are parallel to bedding plane like this, and you take an average of this whole sequence, guess what? The electrical resistivity that the tool is going to measure is not going to be either the sandstone resistivity or the shale resistivity. It's actually going to be lower than either one of those. In this example, for those calculations with 50% proportions, it becomes 1.8 ohmmeters. 1.8. You can actually do the calculation if you use a parallel circuit. So what happens if you take 1.8 ohmmeters and naively, you have not taken this class, but naively you go and plug this number into Archie's equation instead of the 10. Everything else the same. You have the porosity the same, you have the RW the same, or the A, M, and N. All of those parameters are the same. Then what's going to happen is that because the resistivity is so low compared to the actual resistivity of the sandstone, you are going to erroneously conclude that the sandstone has very high water saturation, which is not the case. You see, all of these sandstones are hydrocarbon saturated, but because of the intervening electrical resistivity of the intralayers of shale, the resistivity parallel to bedding plane has been much lower than the arsenic. So what do we do now? Here's the thing. To properly calculate hydrocarbon saturation, what I have to do is I have to take this resistivity and somehow transform it into resistivity of the sand. That's what I'm going to show you how to do. Now, what happens if miraculously you are in modern times and you have an instrument that measures the electrical resistivity perpendicular to bedding plane? Now this is the green color curve. What happens? Well, now this resistivity, because the electrical currents are forced to move perpendicular to bedding plane, it acts like a series circuit, and if you do the calculations for 50% fraction of volumetric concentration of shale, then you're going to see that the value is 5.5 ohmmeters. So this value is actually higher than the parallel to bedding plane resistivity. But it's not yet equal to 10. So you see, we need this value to go to 10 before we can calculate what the volumetric concentration of shale is. To calculate what the saturation of water is in the sandstone fraction of the rock. So we need to do that. And so even though the resistivity perpendicular to bedding plane is closer to the resistivity of the sand, it is not yet that close. So what do we have to do? The answer is we have to make corrections so that the correction will increase the resistivities to give us the resistivity of the sandstone fraction. And once we know the resistivity of the sandstone fraction, then we can use Archie's equation to calculate the hydrocarbon saturation of the sandstone fraction of the rock, similar to what we did before for clean sandstones. So here is the parallel circuit. So if you're looking at the resistivity, which is parallel to bedding plane, that's the equation that we have. It's a parallel circuit. It's almost like you have two resistivities. Here, one is the resistivity of the sandstone, one is the resistivity of the shale. And then the total resistivity is the one that is measured here. Whereas if you measure the vertical resistivity, essentially you have a circuit in series where you have the resistivity of the sandstone and the resistivity of the shale, and the effective resistivity is what you see here. If you remember your classes in basic circuits, that's how it works. That's how it works. So if you have the two measurements, you can solve this equation separately. I mean, like a system of two equations, simultaneous system of equations, and then you can find what the volumetric concentration is of shale and also what the sandstone resistivity is. Of course, the resistivity of the shale is what you measure at a pure shale. That we know how to measure. But most of the time, we have access to only this. Only the new tools measure the vertical resistivity. So, can we solve for our sand? Answer, yes. Very simple. This is the equation. If you solve that equation, the parallel circuit, you go through the algebra, this is what you get. That's the sandstone resistivity. So if you tell me what the measurement is, what the volumetric concentration of shale is, and what the resistivity of the shale is, then I can find our sand. The only complication is that this denominator has to be positive for the resistivities to be physically correct. Have you ever seen negative resistivities? Well, no. So it has to be positive. To be positive, we have to abide by this relationship here. Sometimes I have seen cases where you do this calculation and sometimes it becomes negative. And of course, you have to stop the calculations. You cannot continue, but you have to say, why am I getting values that are negative? And it happens, number one, I have seen this case, if it happens, for instance, when your layers are dipping at an angle and you did not correct the horizontal for the azimuth and dip, because you see the measurements are parallel to bedding plane. So what you have to do is you have to correct. But if you don't have the vertical resistivity, you cannot rotate the vector. So sometimes you have that problem. Second, it happens if your volumetric concentration of shale was not properly calculated. So if you made a mistake by not choosing properly the pure shale or not using the right equations to calculate the volumetric concentration of shale, then that's also possible that you will get a negative value. And last but not least, if when you chose the pure shale point, we're making the assumption that that pure shale point has precisely the same properties as the intralayers of shale that we have here within the volume of investigation. And if that is not the case, if there are discrepancies, then we can have this difference. The other factor that could come into place here is if by any chance the measurements, that's the RH, are noisy or were improperly acquired, then there's also a possibility that you end up with a negative value. But we have to always do reality checks, quality control, make sure that this equation is giving us positive values and the values make sense. Otherwise, get a resistivity that is negative and then you plug it into Archie's equation just because you can. Then you end up with a complex number, and go figure what to do with a complex valued water saturation. Give it to your manager. Here I have a complex valued water saturation, and I also have a complex valued hydrocarbon saturation. It has a real and imaginary part. Go and see your manager. Next day, probably you will be out looking for a job, so I don't recommend that you do calculations with negative resistivities. Anyway, so now, what do we do next? Once you find the resistivity of the sandstone, then this is incorrect. This should be S right here. Then, once you have the resistivity of the sandstone right here, then we can apply Archie's equation. So let's say that you know the Archie's parameter, the A, the M, and the N, all three. And you know electrical resistivity of the water, formation water. Then, because we previously calculated the sandstone porosity, Now we can use this equation, make the assumption that the intralayers of sandstone do not have any grain-coating clay, they're clean, so we can apply this equation. You see, is just to summarize what we did is we knew that in this equation here, in the tools are measuring the horizontal resistivity over here, and that horizontal resistivity is much lower than the sandstone resistivity. So if I plug in 1.8, I'm going to end up with a lot of water. In fact, that was the reason why in the past many people would bypass laminated sections, because if they naively they will take the resistivity log and implement it into Archie's equation. The calculation will give them lots of water, and they say, who wants to produce water sandstones? Not in the hydrocarbon world. So that was the point. But now, after calculating the resistivity of the sand fraction of the rock, resistivity of the sandstone fraction of the rock, and implementing the parallel circuit, then solving it, we find the resistivity of the sand. But we have to be very careful with this equation that comes from solving the parallel circuit, in which we have all the variables that we need. Our horizontal or parallel to bedding plane is a measurement. Just to remind you, our SH is the resistivity of the shell measured across a pure shell, and CSH is the calculated volumetric concentration of shell that we have done here. So this calculation requires that the denominator be positive. It's an important thing. And in order to abide by that assumption, we actually need to abide by the assumption that the volumetric concentration of shell has to be lower than the ratio of the resistivity of the shell over the resistivity of the measurement parallel to bedding plane. This is important because if you don't get a positive value, then this negative value that you get, or zero, when you plug it into Archie's equation shown here, then that's going to give you a complex valued water saturation. Take the square root of a negative number, you get a complex number. And then go figure what it means to have a complex valued water saturation, real and imaginary parts. What does that mean? Well, not in this world. And then suppose that you're not careful with this quality control, and then you continue to do analysis and you propagate these complex valued numbers. So we have to have checks and balances to avoid that. And imagine that you go to your manager and you say, well, I found a complex valued hydrocarbon saturation. And next day, probably you will have all your belongings outside the office waiting for you before you show up to work. So let's not do that. And so it's important. So what are the possibilities? Why is it that sometimes this denominator can be negative? There are at least three possibilities that I know of. One, suppose that the layers, the intralayers of shell are in the sandstone are dipping at an angle which is not negligible. And when we did the analysis, we did not calculate the dip, and therefore we did not correct the measurements that were parallel to bedding plane to be perpendicular to the borehole. We have to correct them to be parallel to bedding plane, so which means that we have to rotate a vector. But suppose that we did not do that rotation and the angle was not negligible, then because of that we might have a problem like this. The second possibility is that the intralayers of shell that we have here do not have the same properties as the shell that we designated to be the pure shell end member of the sequence. So we made a mistake, that was not correct. Third, that the calculation of the volumetric concentration of shell here was not done correctly. Maybe we made a mistake. Maybe the way we calibrated the volumetric concentration of shell with the gamma ray log was not properly done. That's another possibility, so we have to verify that. And you see how in this calculation, any error that you make in the selection of the pure shell and in any error that you make in the violation of the very, very important assumption that all the properties of the pure shale are the same properties as the intralayers of shale that we have in these rocks are the same. If we don't abide by that assumption, all of this is going to snowball like a domino effect, and it will have an implication of not finding a positive number in the denominator of this equation. So that has to be taken into account. And last but not least, there's another possibility, which is that if the measurements acquired by the logging tool, in this case RH, are noisy by some reason or not corrected properly for borehole effects, then obviously that value is going to give you a problem, and that problem might be reflected itself in the negative number. So those are the possibilities. Bottom line is that please check these every single time you calculate, and if you get a negative number, don't go ahead and do calculations with negative numbers, because you're going to get complex valued numbers and nobody knows what to do with them. Now, suppose that you did everything fine and our sand is properly behaved. What you're going to see in this result is that our sand, if you are in the hydrocarbon zone, will be higher than the measurement itself. And that's what we want, because, as I said before, if the measurement is very low, you're going to end up with a lot of water. So we have to correct with that, and hopefully the calculation increases the R sand. And when I plug that value into Arch's equation, then I can now calculate the corresponding water saturation, and 1 minus that will be the hydrocarbon saturation. Now, this equation assumes that I know the Arch's parameters, A, M, and N. I know them from core analysis of some sort. Please note that I have already calculated the sandstone porosity. Please note that the R sand that I have here is the one that came from the solution of the parallel circuit equation. And I also want to point out that I'm assuming, the reason why I'm using Arch's equation is because I'm assuming that as soon as I strip out the effect of the layers of shale, what I have left are the intralayers of sandstone, and I'm making the assumption that those intralayers of sandstone are free of grain coating clay. If those grains have grain coating clay, then I have to apply a second correction. But this equation so far makes the assumption there's not such a thing. Now, what about RW? Well, to calculate RW, what happens is that I have to apply the same set of equations, the same procedure that I just did, the parallel circuit, everything else, in a water-saturated sandstone. If I have a clean sandstone, no shale, then I don't have to make the corrections for shale, and I don't have to use the parallel circuit. But if only thing I have is a shaly sandstone in the water-saturated section of the well, then I have to apply the parallel circuit, eliminate the effect of the lamina of shale in the parallel to bedding plane resistivity, calculate the R sand in the water-saturated sandstone, and implement Arch's equation to calculate RW in that equation. That's how we do it. And that's how the RW comes here. Of course, the RW that we applied in the water-saturated zone, the one that we inferred there, now has to be extrapolated to the hydrocarbon-saturated zone. And if the distance between the water-saturated zone and the hydrocarbon-saturated zone is longer than, let's say, 200 feet under normal geothermal gradients, and then you have to make also corrections for temperature in the extrapolation as we did before for the case of clean sandstone. Last but not least, to calculate the hydrocarbon pore volume, the formula here is slightly different from the formula that we had before. Why? Before, for clean sandstones, that was the formula: hydrocarbon saturation times sandstone porosity. That's what we did. But sandstone porosity here is the one that we calculated. But now remember that because we have all of these lamina of shale here, when you take a volume, the volume will include the lamina of sandstone and shale. So to properly calculate the volume of the fluids per unit length, per unit depth, yes. In this example, we have to eliminate the contribution in the volume from the layers of shale. And that's the reason why we have to adapt the formula to include this last factor over here. So that when applying that factor, essentially you end up with the fraction of hydrocarbon per unit volume that is contained in the lamina of sandstone alone. That's an important remark. Now, when you got that, the next step is to calculate, next and final, is to calculate hydrocarbon density. How do we do that? Well, there are 2 or 3 steps to do that. First of all, the density measurement here, because of the mixing law, is a mixture of the sandstone density and the shale density. Shale density can be calculated or measured directly at the pure shale point. If we have the density porosity measurement in the pure shale, we can convert it back to density of shale. Similar, the sandstone density, the ball density is the measurement itself. If the measurement is given in sandstone porosity units, we have to convert it back to density, ball density, in exactly the same way we have done it before with previous examples. And the CSH here is the volumetric concentration of shale that we calculated with the gamma ray law. So this is just another mixing law. That's the mixing law that I showed before. So we solve for sandstone density from this formula. And now, from that solution, we realize that the sandstone density is a weighted volumetric average of the porosity of the sandstone, which we calculated before, the density of the fluid that we have in the sandstone, and also the fraction, the solid fraction, which is the density of the matrix. If we know the density of the matrix, let's say that we're in a pseudo-cyclastic sequence, then the density of the grains will be very close to 2.65 grams per cubic centimeter. So that's what we assume. If not, well, we have to have a better indication of the density of the matrix. But let's say that we're in a pseudo-cyclastic sequence, so that's easily obtained. So then the sandstone density that we calculated before is implemented here. We solve for the density of the fluid from this equation, and this is the solution. So make sure that this density of the fluid is slightly lower than 1, otherwise we're going to have problems. So we have to have checks and balances. And now the density of the fluid, we go and understand that that fluid might be a combination of water and hydrocarbons. And if we know SW that we calculated from Arch's equation, then we can plug that in this formula where we have another weighted average in saturations, where we have the density of the hydrocarbon and we have the density of the water. If we make the assumption that this is not very salty water, this will be very close to 1.0 grams per cubic centimeter. Or if it's salty, then we have to correct for that slightly, 1.05 or so. And the density of the fluid is what we calculated before. So I go ahead and solve that equation and I get the density of the hydrocarbon. So it's a very tortuous path to get it, but that's how we do it. So now we have everything that we promised that we were going to do. We calculated volumetric concentration of shale. We went to the calculation of the sandstone porosity by making corrections to the neutron and density logs for the fraction of, or the volumetric concentration of shale. We did that correction. We show you how to implement that correction in water saturated sandstones, and as a consequence we got a formula that was easy to digest for an alternative way to calculate volumetric concentration of shale in water saturated sandstones. And then we use the fact that we have an isotropic electrical resistivity in these sandstone shale-laminated sequences to use the parallel to bedding plane resistivity in an analog of a parallel circuit of resistances. And that gave us the estimation of sandstone resistivity. From the sandstone resistivity implemented into Arch's equation, we calculated the water saturation in the sandstone fraction of the rock, and we calculated hydrocarbon per volume, and the calculation of hydrocarbon per volume gave us the possibility also to calculate hydrocarbon density. via this formula. So, in summary, that's what we are going to implement with the example. The first thing, the most important thing, is to detect, identify where the pure shale is. This is perhaps the most important thing, because everything else that follows from this analysis will be a consequence of that selection. And once we select it, we need to make readings of everything: the resistivity of the shell, the gamma ray log of the shell, the neutron and density porosity logs across the shell, and so forth. Then the entire sequence, we calculate volumetric concentration of shell, helped by or guided by the gamma ray log. I show you two cases, two possibilities of calculation. One is to use the neutron and density logs in a water saturated sandstone, or if we have a clean sandstone, then we can use the gamma ray logs to calculate the volumetric concentration of shell using the linear mixing law. Then subsequently, we have to take into account the fact that electrical resistivity is an anisotropic property, in which case we have to realize that most of the commercial measurements give you access to the electrical resistivity parallel to bedding plane, and that parallel resistivity to bedding plane is obtained conceptually from an equivalent parallel circuit, where we have on one side the resistivity of the shell and on the other the resistivity of the sandstone, weighted by their volumetric concentration. So we use that to calculate the resistivity of the sandstone. And from the resistivity of the sandstone, we can either calculate resistivity of formation water, if we're in a water saturated sandstone, or the water saturation of a hydrocarbon saturated sandstone. At the same time, I show you how to calculate the sandstone porosity by making corrections of the neutron and density logs. And the calculations were or could be specialized for the case of a water saturated sandstone with some consequences. And I also show you how to calculate hydrocarbon per volume by making a correction for the fraction of sandstone that we have in a unity volume of rock. And finally, we calculated hydrocarbon density. And then that's it. We are done, and we're now ready to do the exercise. I have some review questions, and the review questions are essentially the most important elements of this conceptual analysis before we go into solving the log example. And I just want to conclude this presentation with a very important conceptual remark, that some of you are going to be doing reservoir simulation where, for instance, you have an injection well here, and then you have a production well on the other hand, and then you have what the flow rates are. And when you do this on a computer, you pixelize everything in between so that you can propagate the flow conditions. You can perform the fluid transfer on the computer. Of course, I'm defining this in a very rudimentary way over here. But what I want to point out is this: when you do this analysis of how fluids move in the rocks between two wells, you don't have the luxury of having too many cells to have super fine detail in the cells, because that will entail a lot of computer memory and also a lot of CPU time to do that. So if I do an enlargement of this cell here, suppose that you are in a sandstone shale laminated sequence that we have studied here. So what's going to happen is this: you're not going to have the memory to include the fine lamina one by one and to be able to propagate or to quantify how the fluids are going to move. You are not going to have that. So what you have to do then is to work with the memory you have, and to do that you have to enter in this cube or pixel so-called effective medium properties or effective properties. And then to do that, it's similar to what we do with the we upscale. But the important thing is this: what am I going to do when I have sandstone shale laminated sequence. First of all, if you're going to enter any value porosity here, please make sure that the porosity has been properly material balanced. In other words, that you have already taken into account what the total porosity is, what the fraction of the shale is, and so forth, so on. And material balance has to be enforced, similar for irreducible water saturation, similar for capillary pressure. And the other thing that is very important is that once we have this situation of highly laminated sandstone shale sequences, then the permeability will have the properties of being directional. You will have one permeability perpendicular to bedding plane and one permeability parallel to bedding plane. So we have to upscale the properties in with the proper context, which is the context of sandstone shale laminated sequences. So please remember all the calculations that we did today, and remember how, if you're going to implement any flow calculations at the reservoir scale between wells to analyze and predict how the fluids are going to move as a function of time once you begin primary or secondary production operations, it's important to understand what properties will be allocated to a particular pixel so that the upscaling effect is consistent with all the petrophysical properties that we know exist in a sandstone shale laminated sequence. And with that thought in mind, we are now going to move into the log analysis. So please get your handout ready. It has already been worked out for you, and I'm going to follow the handout, take you step by step, and we're going to use a log example that is in compendium part 2, pages 1 to 3, and those are the pages that we have done before. Okay, so let's do it.